This is the vocabulary talk on waves, and just some basic vocabulary that we'll be using in other videos and as well as the labs. So first one I want to talk about is frequency of a wave. Frequency, well, just like the name implies, it's how often something happens. And so the frequency of a wave is basically how many oscillations does it do each second. Now the classic units, the SI units of frequency are Hertz. I assume most of you actually heard of Hertz at some point. H-E-R-T-Z, honoring Heinrich Hertz, one of the physicists who dealt with a lot with waves, electromagnetic waves specifically. Anyway, so frequency is the first vocabulary word. The symbol typically used for frequency is F. You will sometimes see in books the frequency, they'll use the nu. That's what a nu looks like right there. I don't use it because it looks too much like a V, but if you're looking at some textbooks, you might see the Greek letter nu. But frequency, F, that's the number of oscillations per second. The next one is period. Period deals with a period of time. It is represented by a capital T, not a lowercase t. Lowercase t is generic time. Period is represented by a capital T, also used for tension, but it depends on context. And period is how many seconds it takes for an oscillation to happen. So if I'm producing 5 waves per second, well, that's my frequency. If I'm producing 5 waves a second, that means that each wave, the time it takes for me to produce the next wave is 0.2 seconds. So that's my period is 0.2 seconds. Just a little bit of math in just a second. Another key vocabulary word is amplitude. Now I don't have a symbol after amplitude because it really does depend. Capital A is often used, sometimes X, sometimes X max, X sub with subscript max. That's amplitude. Amplitude has, from a math point of view, it's basically it tells you the maximum and minimum of a function. However, that doesn't really help you right here. So it depends upon what we're talking about. If I'm shouting at you, then the sound wave has a greater amplitude than if I'm talking softly. So this is going to be a lower amplitude than this. However, if I'm dealing with a transverse wave, all right, I have a certain amplitude, and it's an indication of how far it is from what sort of normal non-movement to the maximum displacement of the particle. And so that has an amplitude right there, and that has a greater amplitude because it's getting farther off of equilibrium officially. So that's amplitude. So it's how high or how loud, or it depends upon what the context is, which the official definition, the non-math definition. Now, the last major vocabulary word to deal with here is wavelength. Wavelength is the distance from a peak to a peak on a wave, or a trough to a trough, or some point on a wave to the corresponding part on the next wave. Wavelength is a distance thing. So frequency, Hertz, period is a time, wavelength is a distance. It's the distance from one wave to the next wave. And so the symbol that is used here is the lowercase lambda. And I can't remember what Hewitt uses, but the lowercase lambda is what I tend to use. And so it looks, as one student unfortunately put it, the drunk T, like a T that's fallen over. But I prefer to think of it as a small uppercase gamma with a long strand of hair blowing in the wind. So wavelength. Now the quick relationship between these is that the frequency and the period are just reciprocals of one another. So that's how I knew that if I was producing 5 waves each second, which is the frequency, then the period is 0.2, because if I take that 5 and I flip it upside down, I now have 1/5, which as a decimal is 0.2. So my frequency is 5 Hertz, my period is 0.2 seconds. And so they're reciprocals. So the frequency is just 1 over the period, and the period is just 1 over the frequency. And the last one brings in the wavelength, is that the speed of the wave is equal to the frequency times the wavelength. All this is just distance over time. Because if you recall, frequency is 1 over the period. So just a quick substitution there. Frequency is 1 divided by the period times the wavelength. Well, let's think about that. The wavelength, that's how long, that's the distance from one wave being produced to the second wave being produced. And period, that's how long it takes. So if I have a wave that's traveling along, then the distance it travels in one wavelength, well, how much time, that's the distance, and the time is the period. And so we end up with and so the speed is just the wavelength over the period, which is just the distance over the time. The reason why I had the bar there, I originally started drawing an arrow, but it really is distance over time. Not worrying about direction. Because frankly, waves travel in this one direction until they bounce off something, and then that's a different problem. But we'll talk about reflection and those type things in a different lecture.